Welcome to the Explainer. Today, we're cracking open the programmer's toolbox to get a look at the invisible architecture that powers pretty much all the software you use every single day.
You ever wonder how that happens? How that undo feature works so fast? It's not magic, I promise. The answer lies in something called data structures. Think of them as the invisible skeleton that holds all software together. Yeah, they're basically the digital Lego blocks that build every single app you use. They are the fundamental tools for organizing all that chaos of information. And today, we're going to fill your toolbox right up.
All right, first up, let's start with the most foundational structures, the ones that organize data in a simple, linear way.
So what's an array? Well, it's really all about order and efficiency. There are two things you absolutely have to remember about them. Their size is fixed, and all of its elements are stored right next to each other, back to back, in a single block of memory.
And this is a great way to think about it. It's just like a filing cabinet with numbered drawers. Since every drawer has a number, we call that the index, the computer can do a super simple calculation to jump directly to any item it needs. That right there is an array's superpower, incredibly fast access.
Okay, but here's the catch. This is where we see the big trade-off. See that O of 1 for access? That's just a fancy way of saying it's constant time, which means it's always super fast no matter how big the array gets. But look at insertion. It says O of n. That n means the time it takes is directly related to the number of items. The more stuff you have, the slower it gets. And why is that? Well, to add one thing at the beginning, you literally have to shift every single other element down one spot. It's painfully slow.
So what do you do when that filing cabinet is full? Or what if you need to stick a new file right in the middle? This is where that rigid structure of a basic array really becomes a problem. And that leads us right to our next tool.
So this is how modern programming languages kind of cheat. Things like an ArrayList, they seem flexible, right? But really, under the hood, they're just playing a clever trick. When that internal array gets full, they secretly create a whole new, bigger one, usually about 1.5 times bigger, and then they have to copy every single element from the old one to the new one. It works, but that copying part, it can bring your whole application to a grinding halt if you're not careful.
Okay, now let's talk about a completely different philosophy. If an array is all about keeping everything neatly packed together, a linked list could not care less. Its elements, which we call nodes, can be scattered literally anywhere in your computer's memory. The scavenger hunt analogy is perfect. Each node holds its data, plus a little pointer that just says, okay, the next clue is over there. And this is what makes it so incredibly flexible. You want to add a new clue right in the middle of the hunt? No problem. You just change the pointers on the clues before and after it. That's it. You're not moving the entire hunt. Compare that to the array, where you'd have to shift every single file in the cabinet. It's a world of difference.
And so here it is, your first major choice as a developer. Do you want an array with its lightning-fast O of 1 access, but hates any kind of change? Or do you want a linked list where finding something might be a slow O of n journey, but once you find it, inserting or deleting is basically instant? It's all about the trade-offs.
All right, let's move on. We're going to look at two specialized linear structures now. These are less about general-purpose storage and more about enforcing one specific rule for how you add and remove data.
First up is the stack, and it follows one simple principle. LIFO, last in, first out. That's it. That is the one and only rule. Whatever you just put on top is the very first thing that has to come off. The stack of plates analogy is perfect. You add a plate to the top, you take a plate from the top. You can't just pull one from the bottom, right? The whole thing would crash. And it's this simple, kind of restrictive rule that makes stacks absolutely perfect for certain kinds of problems.
And hey, remember our question from the very beginning? There's your answer. That undo feature in your text editor? Classic stack. Every single thing you do, typing a letter, deleting a word, gets pushed onto the stack. When you hit undo, the last action is just popped right off the top. Your browser's back button works the exact same way.
Okay, so now let's flip that rule completely on its head and talk about the queue. It follows the FIFO principle, first in, first out.
Yep, it's just like a line at a coffee shop. The first person who gets in line is the first person to get their coffee. A queue is all about fairness and order. It processes things in the exact sequence they arrived. Super simple, super orderly, and incredibly useful.
Think about it. When you hit print on 5 different documents, you don't just get a random one first, right? No, they all go into a print queue, and they're handled one by one, in the exact order you sent them. That's FIFO in action, and it's what brings order to all that potential chaos.
Okay, so we've pretty much mastered the straight lines.
Now we're going to move on to structures that are a lot smarter, ones that can handle more complex relationships than just what comes next. All right, next up is the hash table, or as you'll often hear it called, a hash map. And I'm not exaggerating when I say this is arguably one of the most important data structures ever invented. Why? It all comes down to one word: speed. On average, finding something, adding something, and deleting something are all O of 1. Constant time. It honestly feels like magic.
The magic dictionary analogy is a great way to think about it. You give it a word, the key, and it instantly gives you back the definition, the value. So how does that magic actually work? Well, it's this really clever thing called a hash function. It takes your key, runs it through a special math formula, and that formula spits out an index, the exact drawer number where your data is stored. There's no searching at all. It just calculates where to go.
Okay, so we've done lines, we've done maps, now let's talk about hierarchy. And that is exactly what trees are for. They're perfect for representing relationships, like the folder structure on your computer, a company's org chart, or yeah, even a family tree.
Now, there are a ton of different kinds of trees, but these are the key players you're going to run into. You've got your basic binary tree, where each node has at most 2 kids. Then you get the binary search tree, or BST, which is special because it keeps everything sorted. That makes searching really fast. But the real workhorse, the one you'll see in a lot of systems, is the balanced BST. See, a regular BST can get all lopsided and become slow, but a balanced tree is smart. It actually rearranges itself as you add things to make sure it stays efficient and guarantees those super fast search times.
Okay, so we have officially filled up the toolbox. Now it's time for the ultimate cheat sheet, the part that tells you exactly which tool to grab for which job. This is the stuff interviewers love to ask about.
Seriously, this chart right here is the key to everything. Let's break it down. You need instant access by an index number. Bam, use an array. You need to be constantly inserting and deleting things from the middle of your collection. That's a job for a linked list. You need to look things up by a key, and it has to be insanely fast. You reach for a hash map every time. And what if you need all that lookup speed, but you also need everything to stay in sorted order? Well, that is the perfect job for a balanced BST.
And listen, for anyone out there prepping for technical interview, this is what it's all about. It is never about just reciting definitions. It's about explaining the why. It's about understanding these trade-offs so well that you can confidently pick the right tool for the job and justify that choice. That's what really separates a good programmer from a great one.
So from now on, the next time you hit that undo button, or watch your social media feed load, or even just browse files on your computer, hopefully you'll see this invisible architecture at work. These aren't just academic concepts. They are the absolute fundamental building blocks of our digital world. The only question left is, now that you've seen the building blocks, what will you build? Thanks for watching The Explainer.